قعدت لكم حطيتهم على يوتيوب the videos تبع chapter 4 تبع chapter 3 اخر فيديوز.
اوكي. دكتور، في تايتلز منهم بالفرنش هو ما قلنا عليه فيهم ايه؟
وين؟
في على اليوتيوب تبعك في كان فيديو بالفرنسي مكتوب التايتل، هو قلنا او ما خصوش فينا؟
غلط بركي مكتوب اي وحده.
هلا بشوف لك، خليك سين.
ما في، انا ما بعلم فرنش. سو اذا بتكون لكم بس انا تبع الجروب ثيوري.
ايه
ريد جروب ما خصكم هذا ماستر كلاس يعني.
ايه انه عم بسأل بس انه بركي انت مغلط بشي ما بعرف.
No, it's M1
اوكي
theory the group. Okay,
مزبوط.
you cannot understand this. It's very complicated. Okay, so can we start? بعد في حدا بده ينضم نشوف. Alright, so we'll start. Okay, now we will start a new chapter. So chapter 5, numerical resolution of first order differential equation. Alright, so in this chapter we will see how to solve a differential equation such as y prime of x, yani the derivative with respect to x of a function y is equal f of x, y of x, and it can depend on x and y of x on an interval x belong to AB. Okay, where AB is a given interval. We have the initial solution y of A is equal to some quantity here. Initial solution that we call y0, right? So basically, in numerical solution, we will also factorize the interval x into n plus 1 points, okay, or into n sub-interval. Okay, so interval AB is this being x1, xn. So in order to solve the differential equation, okay, so we will treat the problem where there exists a solution for this equation. So a sufficient condition that a solution, okay, for this problem exists is that f of x, y of x is a Lipschitz function respect to its second variable y. شو يعني Lipschitz function? We defined before what is a Lipschitz function when we defined the contraction, and we said that the contraction is a Lipschitz function with a variable k or L that is inferior to 1. So a Lipschitz function means that f of x y2 minus f of x y1. Okay, here it's Lipschitz function with respect to the second variable y. And this must be inferior or equal to some quantity L y2 minus y1. Okay.
بس دكتور بهدف شو عم نعمل هون؟
No, I'm introducing what we want to do here. Okay. So the objective of this chapter is to solve a differential equation of this type. So y prime of x is some function of x and y. Okay.
اوكي.
And so that a solution exists for this problem. Okay. So f of x must be a continuous function that is a Lipschitz function per respect to its second variable y. So a solution y exists for this problem. Okay. A Lipschitz function with respect to its second variable y. We saw what is a Lipschitz function when we defined the contraction. We said that g of x is a Lipschitz function where g of x2 minus g of x1 is inferior to L x2 minus x1. Okay, where L was inferior to 1 for a contraction. But a Lipschitz function in general, okay, you have a constant L here, okay, that can be not inferior to 1. But here it must be a Lipschitz function with respect to its second variable y. Yeah, here. So when you make f of x y2 minus f of x y1, this must be inferior to L y2 minus y1. So this is a sufficient condition that a unique solution exists for y of x here. Okay. Now, a second thing that we will we have to care about is that in general, as you will see, that the numerical scheme that we will develop to solve this equation, okay, are iterative scheme. And we discretize here, okay, the points here, the interval x, and we have this first point here, okay. So we have the initial condition, and we will calculate the other points. So in general, okay, uh, there's a condition that we must verify on. We cannot verify it all the time, but there is some scheme that can be stable with respect to round off error, and there is problems, sorry, that can be stable. Yani, for a given problem, it can be stable with respect to round off error or not. So a differential equation is said to be stable with respect to round off error when if we change the initial solution by epsilon, the solution doesn't, and the new solution doesn't differ dramatically from the previous solution. We will see examples about this. لأنه هيدي in general in numerical methods, when you define an initial condition, we saw that in the first chapter, okay, a given number is represented in computer with some precision. This precision that depends on the floating number representation. So basically, you're making an error on the initial solution. So when you make an error on the initial solution, if your differential equation, your differential problem can lead to a completely different solution than the solution that is okay than the real solution, right? And this is due to the fact that the error accumulates, okay, during the numerical scheme, and you diverge completely from the exact solution. So if the exact solution, for example, is like this, you can start and then you can diverge from the solution. We will see that this is due to the fact that, okay, that you have an error on the initial solution. And if you have an error on the initial solution, okay, and your equation is such that the error accumulates, okay, dramatically, then you can diverge from the solution. All right, so let's give some example now. So this is said to be a Cauchy problem, okay, when the initial solution is known. This is the initial condition here. Okay, this type of differential equation is said to be a Cauchy problem. So let's give some example of differential equations or of Cauchy problems. Do you understand? Okay. What kind of problem you can have when you will try to numerically solve these problems? Like I said, numerical solution. So we start from, okay, a given point, and then we calculate the other points in general if it's a direct method from this point, and then the next point from this point, and etc. We'll see that. So some example, okay. So let's take, for example, the problem y prime of x is equal minus y minus x y of x, where x belong to 0, 1, okay, and y of 0 is equal to 1. Now, the analytical solution first that's before the analytical solution. Let's see if this is a Lipschitz problem. So the function here, f of xy, is minus xy, right? So if you take absolute value of x, y2 minus f of x, y1, you get absolute value of x, y2 minus y1. And because x is bounded, so this is inferior or equal to y2 minus y1, because the maximum value of x is 1. So this is inferior or equal to y2 minus y1. All right, so this is a Lipschitz function with respect to its second variable. So a unique solution exists here.
بس دكتور شو الكونديشن كرمال تكون لبشتز؟
That f of x y2 minus f of x y1 is inferior or equal to L y2 minus y1.
اوكي وهون بالاكزامبل طلعت L1 صح؟
Yeah.
اوكي.
Yeah. This is a Lipschitz. Okay, this is even a contraction. I mean, okay, with respect to y. No, this is when the quantity is inferior to 1, it's a contraction. In any case, the reason that we use numerical method is that in general we cannot find an analytical solution. But in the example that I will give you, okay, I will give you example where the analytical solution exists. Okay, so we can compare to the analytical solution when we solve. When we use the numerical method, after you can solve any differential equation, even differential equation where you cannot find the analytical solution. Okay, so let's try to find the analytical solution. Here it's very easy to evaluate the analytical solution because it's dy over dx is equal to minus x y. So now you can separate. This is a differential equation that is separable. Okay, so you can separate it. So you can write dy over y is equal minus x dx. And then you can integrate here. So you get log of y is equal to minus x squared over 2 plus some constant. And then you take the exponential of this, and then you get exponential log of y and y. Okay, is equal exponential minus x squared over 2 exponential c. Now, exponential c is a constant, we'll call it k, so it's k exponential minus x squared over 2. Okay, and now we will apply the initial solution. So y is 0, y of 0 is equal to 1. Then we can find k is equal to 1. Okay, so the solution for this problem is y of x is exponential minus x squared over 2. Right. Now, if instead of 1 here, you have 1 plus some epsilon, okay, you can check now the stability with respect to initial solution. Okay, so if instead of y of 0 is equal to 1, I have y of 0 is equal to 1 plus epsilon. And I repeat, the facts why we explore this is because the computer doesn't represent a number with infinite precision. So the initial solution is always represented in a computer with some round of error epsilon. So we want to see if the solution in this case will differ, okay, dramatically from or non-linearly, okay, per respect to x, okay, when we change the initial solution. So now if you change the initial solution, so y of 0 is equal 1 plus epsilon, so 1 plus epsilon is equal to, in this case, k, all right? So it's k exponential minus 0, so 1. So k is equal 1 plus epsilon. So in this case that we have then the initial solution when the solution when the initial solution is changed by vector is epsilon is 1 plus epsilon exponential minus x squared over 2. So here in this case, this scheme is, or this problem is stable per respect to round off error, because when x increases, the error does not increase exponentially or dramatically. Okay, it even decreases with x, which is okay, very good. So this type of problem, you will not have a problem even with the most basic numerical method. You will not have any problem solving this type of problem, right? So of course, like I said, this you cannot, the stability per respect to initial solution, you cannot verify it unless you have the analytical solution. This is just to give you an example that some problem can be stable, some problem can not be stable. So this is very stable, okay, with respect to initial solution, because the error, so we had before y of x is, so this is y, okay, exponential minus x prime over 2 and plus epsilon exponential minus x squared over 2. So this is the error on the function y of x when x, okay, increases, and you see that it's bounded, the error is bounded by epsilon, the error on y of x, okay, is bounded by epsilon. Now this is not always the case, so we'll take another example now. Just like, is it okay? Somebody has any questions?
No questions.
Let's take another example. All right, so example 2, y prime of x is equal x y squared, no matter what x belong to 0a, and y0 is equal to 1. Okay, so now if you want to find the analytical solution here, okay, so the analytical solution here, it's dy over dx. Also, it's a separable this here. Okay, so it's x dx. So this is one. So now when you integrate this, you get here minus 1 over y is equal to x squared over 2 plus some constants. Okay, and means that y is 1 over x squared over 2 plus c, okay, minus, okay. Now if I take y of 0 is equal to 1, okay, then y of 0, 0 means that minus 1 over c is equal to 1, and c is equal to minus 1. Then the solution y of x is 1 over 1 minus x squared over 2. Now, as you see that here we have a divergence for x equals plus or minus square root of 2, okay, when this term comes to 0. So this is this, okay, problem where is already, okay, we already posed some problem numerically, because you have a solution that diverge like this, right? This will already cause some problem. Okay, now let's see if the Lipschitz condition is verified. So if I take now f of x, so this is f of x, f of x is equal to xy square here, f of xy, excuse me. So f of x y2 minus f of x y1 in absolute value, it's equal x in absolute value y2 square minus y1 square, and this is x y2 minus y1 by y2 plus y1. But you see that this is not a Lipschitz function, because even though a solution, analytical solution exists here, okay, unique analytical solution, it's not a Lipschitz function. Okay, so because here y2 minus y2 plus y1 is not bounded by here any value, because the y can go to infinity in any case here when it's close to square root of 2, right? So this problem will cause already some problem here to solve it numerically because of this divergence here, okay, and because it's not a Lipschitz function, but mainly because of the divergence, okay, for x around plus square root of 2. Now, if it's okay, if you solve the solution, for example, for x between 0 and 1, where it's before the square root of 2, then it should be okay, okay, to use the numerical method. Okay, now let's take an example 3 here. Some other also differential equation. Let's take the case where y prime of x is equal to 5y minus 6 exponential minus x. Y of 0 is equal to 1. Okay, so this type of problem can be solved by separating the problem using homogeneous equation and a particular solution, or using what we call the variation of the constant. Okay, so I will use the homogeneous equation and variation of the constant because it's general method. Okay, so homogeneous equation. So let's find the analytical solution. So for the analytical solution, we use the homogeneous equation. Alright, so in the homogeneous equation here, okay, so I have y prime of x plus minus 5y equals 0. So here, same thing. This is a separable, the homogeneous equation. So you have dy over dx is equal to 5y. So dy over y is 5 dx. So now when you integrate, so you get y, log of y is 5x plus some constant, and y is exponential c exponential 5x. So this is k exponential 5x. Right. Now, so because we have here another term that depends of x, we will use the method that is called the variation of the constant. So this constant in this problem, now the general solution, we can, not for the homogeneous equation, but for the general equation, we can express it as y is equal k of x exponential 5x. And we will try to find this k of x here, what is, okay, by replacing into the main equation. Okay, so we replace into the main equation y prime of x is equal 5y minus 6 exponential minus x. Okay, so now we will derive this equation. So it gives me k prime of x exponential 5x plus k of x multiplied by the derivative of this, so it's 5e5x equals 5k of x exponential 5x minus 6e minus x. So this and this, okay. So here I can express k prime of x now is equal to what did I do here? Right, so I have that k prime of x is equal to exponential minus
6x.
6 minus 6x. Okay. Now, this means that k of x is equal to exponential minus 6x plus some constant, right? Now you replace now this k of x into your solution now here, so y of x, and you apply the initial solution. So y of x is equal to exponential minus 6x plus c, okay, exponential 5x. All right. And now applying the initial solution, and now initial solution, y of 0 is equal to 1, right? This is the initial solution. Okay. So I will find 1 plus c is equal to 1, and c equals 0, right?
Mhm.
Okay. So y of x is equal to exponential minus x multiplied by exponential 5x, so it's equal to exponential
Minus.
Okay, so you could have now here, instead of using the method of variation of the constant, use here a particular solution. So you can suppose that there is a particular solution. Okay, find a particular solution and add it to the general solution, and apply the initial condition. And in this case, the initial solution is of the type exponential minus x because of it. Okay, and then, but this is a more general method that, okay, works. So now let's see. We can verify if this is a Lipschitz function. Okay, so did I give an interval here? Okay, so let's say the interval is x 0 some quantity a. Okay. So this is, let's just waiting for the rest to join.
دكتور حنطول؟
ليش معكم بعدين؟
ما عندنا صف، بس أنا عندي شيء عم شوف إذا معقول نطول أو لا.
بعد نص ساعة.
Okay.
Okay. Now we were discussing this problem. So now let's see. Now, is it the Lipschitz function with respect to second variable? Is f of xy. F of xy was here, okay, simply 5y minus 6 exponential minus x. This is, you can see that it's a Lipschitz function, so okay. This is equal to 5 y2 minus y1. Okay, so it's a Lipschitz function perspective. So we don't have a problem here, and a unique solution exists. Okay, and but now let's see the stability with respect to initial condition. Okay, so basically this was the general solution. Y of x is equal, okay, to exponential minus x plus c, okay, exponential 5x. Okay, and when we had y of 0 is equal to 1, then we got exponential minus x. But now if we have y of 0 is equal 1 plus epsilon, epsilon is some round of error. It is to the floating number representation in the computer. Okay, so if we now have y of 0 is equal 1 plus epsilon instead of 1, then we have that exponential minus here 1 plus c, okay, multiplied by 1 is equal 1 plus epsilon. So c is equal to epsilon. Okay. So now if y of 0 is 1 plus epsilon, the solution is changed into exponential minus x, okay, plus epsilon exponential 5x, right? So you can see here that the error on y, if there is an error on the initial solution, okay, epsilon,
شو بالحانة؟
اختفى.
تكون راحت الكهرباء عادي. ضيق لي خلقي.
بيفقع القلب.
تخيل تكون ريكوردينج بس.
يلا تنفل.
hello, I'm sorry.
Hello.
I lost the internet.
It's okay.
So now when we change the solution by the initial condition by epsilon.
As Dr. ما في screen.
Yes. When you change the initial solution by epsilon, the solution y changed into exponential x, okay, which was the solution for y of 0 equals 1 plus epsilon exponential 5x. So the error on y, okay, increases, okay, exponentially with the round of error of the initial solution epsilon. So this problem is very challenging to solve, okay, numerically. And we will try to solve this problem numerically, and we will see that the solution will diverge, okay, with the x. So when x increases, we will have, okay, the solution will differ from the exponential minus x significantly. And so even with a slight, okay, error, okay, that the solution will differ, and this is due to, like I said, the round of error, okay, in computer. All right. So due to the round of error, due to the floating number representation, or due to the fact that the computer cannot represent number with infinite precision. So when you have an error at a given x, this will increase, okay, exponentially with epsilon for this type of problem. Okay, so you can see that when we will try to solve numerically differential equation, we can have some problem, okay, due to the fact that, or the solution, okay, sometimes is not diverges at some point, like the previous example, or because, okay, we have the fact that the solution, okay, diverges when we have some initial condition, or we have some error on the initial condition. Okay, so now we will discuss the principle of the numerical methods. Okay, so like I said, the numerical methods consist of, so if we want to find the solution on a given interval a, b, we discretize this interval into n plus 1 point, or n steps. Okay, in general, steps being h here. Okay, this is the first point, this is the point n plus 1, and this is a point here xi. Okay, h is equal to b minus a over n, the total number of points here, and total number of sub-interval. And for Cauchy problem, we have, okay, the initial solution y1, which is, okay, y of x1. Okay, so there is two types, okay, of numerical method. So numerical method consists of finding, okay, the values for the function at any other points here of this interval ab. Okay, so we will construct, for example, if we have here, let's take it a little bit down here. Okay, so if we have this solution, we'll construct this one, this point, this point, this point, this point, and we will get the total function, all right, for example. Okay, but starting from one point here. So this is for the Cauchy problem. Sometimes you have boundary problem where you have this solution and this solution here at the end. But in this chapter, we'll discuss, okay, initial conditions problem, which are Cauchy problem, where you have the initial condition or initial solution here, okay, and then you try to construct the other points. So there are two types of numerical methods. Ones that are called explicit so in the explicit method, the solution yi and y of xi, okay, is calculated directly from the solutions from the points the yi minus 1, yi minus 2, and the previous points. There is a solution who are here, okay? So we calculate this point from this previous point, this point from this previous point. It can depend on this point and these 2 points, okay? This one can depend on this one, this one, this one, or extra. So we can calculate directly the points, the y of xi, yi, okay, from the previous point. So we do this iteratively. Like I said, we calculate this point from this one from these 2, this one from the previous, and etc. So the solution yi, okay, depends on all the previous points. Can depend upon, okay, so this will go from k equals 0, okay, phi of xi minus k, okay, yi minus k. And this means that there is a function here that relates, okay, this point to all the previous points, okay. Here it's k equals 0, yes, all right.
Okay.
I didn't define this function. The numerical method will define this function. And like I said, this point can depend upon just the previous point or can depend on several points. Okay, so the point xi can depend just on this point for the numerical method, or can depend on the several points. This function here, or the relationship between this points and the previous points, this is the numerical method that will define this function phi. Okay, so for each numerical method, we have a different relationship between this points and the previous points. And we'll see how to derive each of the numerical methods starting by the steps. Now, the implicit method in the implicit method, okay, the solution at step I, or the solution yi, can depend on the future points, or say yi plus 1, yi plus 2, etc. Okay, which we don't have it. We don't have these points. Okay, so here we cannot apply just a direct method, like, okay, because if you want to calculate, for example, we have this point, we want to calculate this point, and in the implicit method, this points depends upon this points and this point, but this one we don't have it, we didn't calculate it still. So in this case, okay, you cannot solve, like, derive these points directly. You need to solve a nonlinear, or a system of nonlinear equation. In the general case, okay, the system of linear equation also. Okay. So these are more complicated to implement, but they have some advantage with respect to the explicit. Okay, you will see that in third year when you will apply implicit methods with Joseph Trem. Okay, and you will see that they are more stable with respect to the spacing. Okay, so they can be more accurate, okay, than the explicit method for a given here step h, a given spacing h. All right, so now let's see the most basic method, which is the Euler method. So the Euler method is the most basic it's the simplest, but okay, the error here is, so we have the following system, whereas y of a is equal to, okay, y0 is x belong to ab. So here, like I said, we discretize our interval here. Okay, ab, okay, into points, okay, of step h. This is x1, this is xn plus 1. Okay, so the Euler method is very simple, consists of finding the points yi plus 1 from the points yi by applying yi plus 1 is equal to yi plus h f of xi yi, where f is this function here, and h is the step, okay, or the spacing between the points. So if you have the first point here, let's call it here. It's better than y0, right? So y1 is y of x1, okay. First point. So we have the first point here, okay. Now we construct the next point. So this is, we have the initial solution y of at x1. We construct y at x2 using this formula. So y2 is equal to y1 plus h f of x1 y1. Okay, so y2 is equal to y1 plus h f of x1 y1, etc. So implementing this in MATLAB is straightforward. Now I will show you how to derive this Euler method. It's very simple. There's different methods to derive, different ways to derive this method. It's very simple. But implementing this in MATLAB is very straightforward. So you define, for example, n equals 100, the number of points. You define your vector AB, for example, let's say, okay, A equals 0, B equals 1. Okay, just for example, you define the vector X, okay. So yeah, you define H here. H is equal, so this is the number of sub-interval here, B minus A over N, okay. And then you get the vector X of, let's say, okay, N plus 1 point. So A, B, right? And then you make a for loop here. Okay, you have that y, you need to calculate y at these points now. Okay, you take y of 1 is equal to the initial solution, I don't know, let's say 1, okay. Okay, and then you make 4, okay, I equals 1 till n, and then you make y of I plus 1 is equal y I plus, okay, f of x I y I, and here you get your vector y. You can plot x, y, and you get your function. Okay. So this is a direct method, okay, where y I plus 1 depends on yi on the previous points only. So yi plus h of x I yi. So how to derive now this Euler method? Well, we can derive the Euler methods from, okay, using in many different ways. So that's the derivation from the Taylor expansion. So you have that yi plus 1 is equal to y of xi plus h. Okay, this is the definition of y plus 1. It's y of xi plus h. It's equal to y of xi plus y prime at the point xi, okay, multiplied by h plus higher order term 1/2 okay, y second h squared extra that we neglect here. Okay, this is higher order term. So the Euler method is a first order method. Okay, and that's why it's not so accurate, but it works in the case where your spacing h is small and you don't have error problems of divergence in your problem and things like that, so it works. So basically you have, so yi plus 1 is equal to yi, okay, y of xi is yi, plus y prime of xi, this is f of xi yi, right? Because y prime is f of x y. This is how we can derive the method from the Taylor extension. Now you can derive it similar way from the rectangle left corner, for example. Okay, so I have that y prime of x is equal to f of x y. So then this means that, okay, y of x is the integral, okay, of, I will put the second variable here, dy of t dt, okay, from a to x, okay, and this means that y of I plus 1 is equal to y of xi, yani yi, plus the integral xi till xi plus 1, okay, of f of t y of t dt, okay, because this is the, okay, now if you apply the rectangle left corner, I get that y of I plus 1 is equal to yi plus, and then this was the left corner is h f of xi, okay, yi. Okay, because when you integrate in the left corner, you take just like the, here is just 2 points, so it's h f of xi yi. Okay, so you can get the same expression using the rectangle, for example. Okay, and we'll stop here. Okay, we'll continue next time. All right. Any question now concerning this?
لا ما فيش.
No.
So, right, so we'll end this meeting and see you next week.
Okay.
Did you receive the YouTube? Now I will put them all in one playlist, numerical analysis videos. I don't know if I shared everything. إذا نزلوا كلهم. I will check. هلا بعد في فيديو exercises وقصص هيك ما حطيتهم يعني انه لما كنت عم بحطهم الاكسرسايزز على زوم او شيء عم شوف اذا بنزيدهم بعدين. Okay, that's what you have on YouTube is the courses. Okay? Is the lectures. راح ابعثكم الباوربوينت. Right?
اي باوربوينت تبع اللي عم نعمله هلا او تبع قبل؟
هيدا ما فيه باوربوينت هيدا because it's a lot of equations but الباوربوينت اللي عملناه تبع الانتجريشن حطيت على اليوتيوب الفيديوز تبع all the chapter تبع الانتجريشن. اوكي وحطيت كمان بعد chapter 3 كان في part تبع الزوم مش حاططها. اوكي تبع اللي سكوير تاني بارت سموثينج داتا.
هبعت لنا اياها ليست سكوير.
ايه بس كان في بارت 1 بارت 2 بارت 3 ما
اوكي
اوكي الابلكيشن يعني انه ما كنت حاططها. بعدين شابتر 4 حطيت كل الفيديوز يعني حطيت الريكتانجل ترابيزويد والسيمبسون عملناها هذيك المره.
اوكي
مع you have basically on YouTube. All right. Yeah. See you next time.
Okay.
deal.
Bye.